But she's a longtime collaborator of several Brazilian mathematicians and geometers. And she visited Brazil, IMPA, the University of São Paulo, several times. And she was also here a few weeks ago for this event in São Paulo. So I'm very happy to introduce her to our webinar. And this is the title of our talk, Minimal Graphs with Infinite Boundary Values in Three Manifolds. So Barbara, whenever you're ready, you can present your talk.
Thank you very much, Paolo, and thank you all for the organizer for the invitation. It's a long time that I'm not doing a talk, online talk. Some of you have already listened to my talk in São Paulo. It's very similar, so I'm sorry about that. It will be a little bit boring for the ones that were there. But by the way, it was a so big pleasure to be in that event, a really very nice event. Okay, so let me start. It's always a pleasure to be in Brazil, even if it is online, for an online talk. I will talk about the minimal surfaces in three manifolds. So I will do an introduction first. So a minimal surface in three manifold, we have a three manifold and we have a two-dimensional manifolds inside the three manifold. So everything is Riemannian. We have two Riemannian metrics, and one is the induced metric on the surface. And M is minimal, that is the mean curvature is 0. Okay, so this is a very general setting for the moment. It is well known that the minimal surface may also be characterized as a critical point of the area functional, and sometimes it really minimizes the area functional with respect to compactly supported variation. This is something that one can teach to students, very young students at the second year of university or something. But more precisely, locally, any minimal surface can be seen as a graph of a function that satisfies a certain PDE, a partial differential equation. Because in fact, you can write H, the mean curvatures, in terms of the function that describes the graph, and then you have a second order PDE that is a very special one. If you restrict for the moment yourself to a surface in R3, we are no more in a general manifold, but we are in R3, and we take a graph of a function, then the graph is a minimal surface if U satisfies this equation. It's a very well-known equation. If you look at it a little bit, you see that it is a quasi-linear PDE, because the second derivative appears only linearly. So it's a nice equation, and it's also the nicest thing that this equation has is that it is elliptic. So one can really work. These two characteristics, being elliptic and quasi-linear, in fact, hold in any ambient space and with some different notion of graphs. Because if you are in a different ambient space, you can define different notion of graphs, but you will have, again, a quasi-linear elliptic equation if you consider a minimal surface. Of course, the divergence, the norm will change, but the kind of equation is not very different from this one. You will see that later on. Okay, example of a minimal surfaces, everyone knows about that, but I like to show them just very quickly. We have the catenoid, that is the only one complete that is invariant by rotation in R3. Then there is the helicoid. They are more or less in the same time, at least in the same century. The helicoid is the one that is invariant it's a screw motion. So you take a half line and you rotate and translate along the axis. Then there is an upper surface. Why one shows an upper surface? It's it has more or less 1 century more, but it's also a complete non-embedded example. In fact, topologically, this is a plane, and this is just banded in this way, and there are self-intersections. Okay, if still in the in this century, 1834, there is this further example. This is very nice surface. Is a graph on a chessboard. So it's a nice surface. It was discovered by Shark. We will be back to this example in a while, because before that, I want to show Costa surface. This is particularly interesting in Brazil, because Celso Costa is a Brazilian mathematician that discovered this very nice surface. This was the first example with genus, because in fact this is a torus minus 3 points. The 3 points corresponds to this one that is going to infinity above, this one that is going to minus infinity below, and then there is a and in the middle that is a planar end, something like a plane when you look at it from very far away. And above and below you have like a catenoid, more or less. But there is genus here, so it was the first example with genus, and it took a long time to show that it is an embedded example. Embedded, I mean, you see at finite point it's very easy to see, but that it is embedded at infinity, this was a difficult stuff to show, because if you know a little bit about minimal surface, usually minimal surfaces are given in terms of a Weierstrass representation. Weierstrass representation is something, an integral representation, so it's very hard to prove things about the coordinates when you are far away. Okay, so Shark surface. Let me go back to this nice surface and explain very quickly how Mr. Shark found this surface out. So you take a square on the plane, and you define a function, u of x squared log cosinus x over cosinus y. And if you do the graph, in fact, it is a minimal surface, and it is a piece of Shark. How did Shark discover this surface? In fact, it took the minimal surface equation. I didn't write it explicitly, but if you write down the minimal surface equation, it is a PDE like that. And then instead of trying to solve it like with any function of x and y, he tried to solve it as writing u x y equal to f of x and plus g of y. Okay, and if you try to put in the minimal surface equation the sum, so different, the two functions of the two different variables, and you sum them up, then it's very easy to solve, and you find this. So this is really an exercise that you can give to students. Okay, so then there is a reflection principle, so that you can extend it on the chessboard in the plane. Okay, this was Shark, and now one can ask if one can generalize Shark surface. Okay, so it's a very nice minimal surface. So what happens if the domain is Rother square? What happens if one has more than 4 sides, so you have a polygon? Or may you find a surface that has infinite boundary value, because you see here Shark surface, it's plus infinite, minus infinite, and minus infinite because of the log. It's very easy to see. So this kind of generalization, I mean, may you find the minimal surface with infinite boundary values somewhere and on some shape, no? On a domain of some shape. And also, what happens if one allows finite boundary values somewhere? This is a very nice question, and Jenkins and J, two very productive mathematicians, solved that problem, and it's very nice, the theorem that they prove. So let me just give you some notation. You consider a bounded convex domain omega in R2, whose boundary contains two sets of open straight segment, A1, AK, B1, BL, with the property that no two segment AI and no two segment of the BJ have a common endpoint. And then you have some convex, some open arcs with their endpoints. Of course, they should be convex because you need a convex domain here. This is one of the assumptions. Okay, so you have some part of the boundary that are straight segment and some part that are convex side. The problem of determining a solution of the minimal surface equation in omega, which assume plus infinity on the AI, minus infinity on the BJ, and some continuous data on the arc CS, is known as the Jenkins-Serrin problem. Jenkins and Serrin were able to give a simple, necessary and sufficient condition to solve this problem. Okay, this problem that I wrote here. And the condition depend only on the geometry of the segment AI and BJ.
Barbara, just one question. The property that these two families of segments have means that they're alternated AB, 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 right?
Right.
So they should be an equal number of A's and B's.
No, because you can have the CI in the middle. I mean, if you have only
also, so the boundary is not only A and B.
No.
Okay.
If you have only A and B, it's exactly as you say. But if you have also the CI, you can have some CI in the middle. The important thing is that two of them don't meet it at the convex corner.
Okay.
Two of them. Okay. Okay. So let me just now make a remark that also justify what we are my answer to Paolo as well. If you have two segments, for example, two AI that meet at a point at the convex corner, and you give a plus infinity on the, let's say, A1 and A2, and you give plus infinity on A1, a plus infinity on A2, then by the maximum principle, that is something that it is satisfied by minimal surface, you will have that everything is infinity in the convex hull of the two segments. So you will have infinity also inside your domain, and your solution would explode. Okay, so this is why it's very natural to ask that no two of these segments meet. The same for minus infinity, of course. And the same why one does not give value plus infinity on a convex segment, on the convex curve, because if a solution is plus infinity on a convex curve, then it is plus infinity on the convex hull of the curve. So it's very natural to assume this kind of hypothesis on the domain. Then the theorem. So take any polygon whose vertices are chosen among, you have your domain like that, your omega as we told. And then let P be any polygon whose vertices are chosen among the endpoints of AI and BJ. And you call alpha and beta the total length of the segment AI, which are part of the polygon, and the total length of the BJ, which are part of P. And gamma is the perimeter of P. Of course, if you only have AI and BJ, the polygon could be also your domain, your entire domain, because you take all the sides, for example. But you have also many other polygons inside, inside your domain. Okay, so here is the theorem. If the family of the convex arc is not empty, the Jenkins-Serrin problem is solvable if and only if 2 alpha is smaller than gamma, 2 beta is smaller than gamma, for each polygon chosen as above. If the family is empty, the result is the same, except that if P is the entire boundary of omega, condition 1 should be replaced by alpha equal to beta. And the solution is unique. And of course, it's unique up to translation if the convex part of the boundary is empty, because if you are, this means that you have only plus infinity and minus infinity on the boundary. So of course you can translate as you want, and it's a different solution translated. So it's unique up to translation in this case. So now I'll give you some example, but it's really a very, very simple condition on the length of your inscribed polygon. They also have a less famous generalization to the non-convex case, but this is I'm going to talk about that later on in a more general context. And I want to stress the fact that when you don't have this CI, Jenkins-Serrin proof depends on the fact that the geometry of R2 give you that neither the union of the AI and neither the union of the BJ is connected. Because as there should be a BJ among, or a C among two AI, then it's very easy to see that none of them is connected. But you can imagine that in a different kind of space, this could happen. Okay, we will see some example later on. Okay, but the proof is based on that. It's too much. Depends also on this fact. Okay, so examples. A triangle. A triangle is a very simple example. A triangle like that. I take a triangle and I put plus infinity here, and I take C1 and C2. I'm writing here C1 and C2, even if it is not strictly convex. It's just a stripe, because this means that I give finite boundary value on C1 and finite boundary value here. So let us see the Jenkins-Serrin condition here. The polygon, the only possible polygon here is the triangle. Okay, so alpha is the length of A1. I put A1, but I mean the length. And the gamma is the perimeter of the triangle. So let us write the condition. The condition is gamma larger than 2 alpha. But this is true if and only if C1 plus C2 is larger than A1. And this is the triangular inequality. So this problem is always solvable for any triangle. Okay?
Do you assign the value on C1 and C2?
Yeah, any finite value.
Constant.
Continuous value.
Continuous.
Continuous. Okay. It's enough. Okay. Not constant. You can give constant, but you can take any continuous value. Okay, so another example, a quadrilateral. So A1 and A2 plus infinity, and C1 and C2 continuous boundary value. And now, of course, you have different polygon. One polygon that you have is a triangle. If you take the triangles, if you take the diagonal here, you have the two triangles, but the two diagonals you can take. You have two triangle one, two triangle on the other side. But for the triangle with one side plus infinity, we already have the triangular inequality. So you have no condition. It's for free. So you stay with the entire polygon, the quadrilateral, the rectangle here. So you write the perimeter, A1 plus A2 plus C1 plus C2, and then you take alpha is A1 plus A2, and then the condition is C1 plus C2 larger than A1 plus A2. That is only one condition, but is a condition. So this means that the sides where you have a finite boundary value must be larger than the side where you have infinite boundary value. And this is very natural, because if you have a big part of the boundary that push your solution to infinity, it's very likely that you will have infinity that you don't have a finite solution inside. But like that you have. So this is the Jenkins-Serrin condition in this case. just another condition. For example, if you take a quadrilateral like that, you put plus infinity, minus infinity, minus infinity. The only condition is this one. So that the sum here is equal to the sum of the BI. Okay, I'm going quick here because I just want to go to the last example. Here, for example, A1 plus infinity, A2 plus infinity, B1 minus infinity, B2 minus infinity, and that you take two convex sides like that, and you assume that it's finite here. And that here is very easy to see that if you take this quadrilateral, A1, L2, A2, L1, then the condition is not verified because the AI are too long with respect to the Li. So on this problem has no, the Jenkins-Serrin problem here is not solvable. There is no minimal surface because it's if and only if. So there is no minimal surface that has plus infinity and minus infinity boundary value on this hexagon. And finite boundary value, any finite boundary value on C1 and C2. Okay, so these are examples, but you can create a lot. And just then, many years later, no, some years later, in fact, there was a first generalization by Joyce Brooke, and it did Jenkins-Serrin theorem for constant mean curvature surfaces in R3. There were no more minimal, but constant mean curvature. And it's very nice because, you know, when you are minimal, we put plus infinity and minus infinity on straight segment. And here, as there is constant mean curvature, then you put infinite boundary value on curves that has constant curvature equal to twice the mean curvature. Okay, so arcs of circles.
So here you prescribe the mean curvature.
Yes, you take a constant mean curvature, you prescribe the mean curvature, you're not more mean curvature 0, but it's a positive constant. And then you need, or you prescribe it, but in fact you need that the sides where it's the curve where the surface, where the function go to infinity, the boundary curve, has twice the mean curvature. Okay, so it's this is and the condition is exactly the same on the length as the Jenkins-Serrin condition. Exactly the same condition. So it's very, very interesting. And then there is a generalization to higher dimension. This was done by Umberto Massari and Ermanna Tomaini. One is for the case without convex, without finite boundary value. And the second one is the case where there are all, no, it's the contrary. Massari did the case where you also allow finite boundary value. Tomaini did the case where you don't have finite boundary value. That is harder because everything can go to infinity in that case. You don't have something keeping your solution fixed. So it's, but they succeeded in generalizing this one. And then many years later, in 2002, myself and Rosenberg, we proved the generalization of Jenkins-Serrin theorem in this product space, that is the hyperbolic plane time R. So here it was harder because you have a different kind of, I mean, your domain is in H2. And this time, this was the time where many people in minimal surfaces started to work in this E-kappa tau that later became E-kappa tau spaces that are homogeneous, three-manifold, simply connected, and so on. These are the Thurston geometries, in fact. So this was the first Jenkins-Serrin there in this kind of spaces. And then there are more or less 20 years of 20 years of results about Jenkins-Serrin problem in different ambient spaces for ideal polygon. Because, for example, in H2, you can imagine that you can take a polygon but also a polygon with vertices at infinity. So, and of course, in that case, it's harder. But then, I mean, there are interesting results. But what is very interesting in all of that is that everywhere the condition is the Jenkins-Serrin condition. I mean, it's always the same condition. It's harder to prove, less hard. I mean, it can be harder to prove, but the condition is the same. So Jenkins-Serrin really, their result was far beyond what they were thinking about. I only cite one work instead of 20 years of literature by Mazet, Rodriguez, and Rosenberg. You will see it later because it contains really the seeds of our future work. Because they solve this Jenkins-Serrin problem in M cross R for some cases, in a general product space. But they use something that, I mean, they started to talk about something that we really use. They didn't use finally, but we use that. So you will see why I'm citing this work. Okay, just I was telling you about this ideal polygon stuff, and I want to show you that this minimal surface in H2 cross R, given by Jenkins-Serrin in some sense, were really a very interesting object, because they helped to for example, they helped to disprove a conjecture that goes as follows. In 52, Heinz proved that there is no harmonic diffeomorphism between the Euclidean disk and C. And he proved that. Then in the 90s, Rikschen and Yao conjecture that there is no harmonic diffeomorphism between C and H2. So if you want the disk with the hyperbolic metric. So they were proving something else, and they conjectured this. They were studying harmonic map, and they conjectured this. But then, in fact, Pascal Colin and Aaron Rosenberg disproved the conjecture because they exhibited a minimal graph in H2 cross R with a conformal structure of C. So a complete minimal graph on H2 with a conformal structure of C. And as the projection on the first two coordinates is an harmonic map, so from the surface, with the metric of the surface of your graph, 2H2 is a conformal map, then, is an harmonic map, then this graph gave an harmonic diffeomorphism between C and H2, the disk with the hyperbolic metric. And how did they compute this? How did they produce this graph? This graph was just a Jenkins-Serrin graph in H2 cross R with over an ideal polygon. So you take an ideal polygon, any ideal polygon, you can prove that there is a Jenkins-Serrin solution. So plus infinity, minus infinity, plus infinity, minus infinity. And then you increase the number of vertices. And finally, if you prove that everything works, there is a convergence argument, a strong convergence argument, you can prove that you have a graph on H2. And you can prove that the conformal structure is C, so you have a counterexample to this conjecture. Okay, and of course, this is Annals of Mathematics. This is for Enrique, because he already asked me why. This is very mysterious. Why I'm writing like that, because it's short. This is Annals of Mathematics. If you want to know some other journal, you can ask me.
Could be Acta Mathematica.
That's true. It could be Acta Mathematica. You're right. So it's really.
You should put at least lowercase o in the middle.
You're right. You're right. I didn't think that this could be Acta Mathematica. That's right. Okay. So let me go to something new. Then, as I told you, there were a lot of results about Jenkins-Serrin theorem in general essentially in product space, essentially. But what changed a lot was the dimension, was the curvature, no, not minimal, but constant mean curvature, and so on. And then we decided to try to solve the Jenkins-Serrin theorem in killing submersion. This is a joint work with a PhD student, Andrea del Prete, and José Miguel Manzano from Granada, from Jaén, sorry. Originally from Granada, but now he's in Jaén. Okay, so let me just tell you about the setting. So what is a killing submersion? You take two Riemannian manifolds of dimension 2 and 3 respectively, and the projection from E to M is a killing submersion. That is a Riemannian submersion whose fibers are the integral curves of a non-vanishing killing vector field defined on your three-dimensional manifold E. So here I recall what is a killing and what is a Riemannian submersion. Okay, so it's not a product, but you have a privileged direction. But the length of this killing vector field is not constant. Is really a very general one. It's non-zero, just non-zero. There is also another way of seeing this very natural notion. That is, you take a three-dimensional manifold and the complete non-zero killing vector field on it, such that the one-parameter group of isometry G associated to Xi acts freely and properly. Then the orbit space E over G that you call M is a well-defined Riemannian manifold, and the quotient map is a Riemannian submersion. You can choose your favorite notion of killing submersion. But you see, it's a three-dimensional space, but it's very general. And why, I mean, you need a privileged direction. This is just because as we are thinking of solving a Jenkins-Serrin problem, we need to be able to give a notion of graph, a good notion of graph. So you need a direction to produce a graph. Examples, you can take any warped product. Of course, the E kappa tau spaces nil and sol that are not products. And any homogeneous manifold homomorphic to R3 and S3, for example, you can give this kind of structure. So it's, I mean, a lot of things. Okay, so let us, before going inside the theorem, the Jenkins-Serrin theorem, let's describe some characteristic of these spaces. So the geometry of any killing submersion, in fact, is encoded in the surface, in the base, where you are projecting, and two geometric functions that are the bundle curvature, that is defined like that, and the mu, that is the norm of your Xi, of the killing vector field. This is the geometry of this killing submersion is very well explained and proved. All this is proved by Lerma and Manzano. This is Annali di matematica pura e applicata. Okay, so you have just to keep in mind the tau and mu. And we also assume that the fiber of pi have infinite length because you want you want that your function can go to infinity. So, or you can also take the universal cover. I mean, but we will assume that the fiber have infinite length. So let us give the notion of graph, a killing graph. You fix a domain, your manifold, and you take an arbitrary zero section, and then you can define the killing graph with respect to this zero section as the surface that is parameterized like this: f of u, fu of omega, fu defined in the domain omega, fu of the point P is is a phi P of u P f0 P. That means you go along the fiber of a certain length that is U of P. So you take a point, you take the fiber over the point, and you go to a certain distance from this zero section. Okay, and the distance is U of P. So it's a very natural notion of graph. And when you write the mean curvature of this graph, you have this equation. So it's again divergence. You have this mu appearing all the time. So this mu, for example, in the case of, in some cases, in the case of a product, it's just 1. So it's constant equal to 1. And then instead of the gradient, you have this generalized gradient. I'm not going to describe exactly how to write this equation and so on, but this is generalized gradient, and it's anyway, you can treat it as a gradient. It contains some distance inside, but it's a gradient. Okay, so this is the equation. As I promised, has the same structure as always, as I promised at the very beginning. It's a divergent structure and so on. Is elliptic and quasi-linear. Okay, so, but there is a mu here. So how this mu enter now in our description? Okay. In fact, we are going to describe on M a different metric that depends on mu. Okay, because you have on M, you have your domain, you have defined your graph, and now you want to understand how to relate it with the mean curvature. So consider a curve gamma on M and the vertical cylinder on it. Vertical cylinder means vertical in the sense pi minus 1 of gamma, where pi is the projection. You are killing projection. And you take N, the unit normal vector field along C. Then the mean curvature of H of C, you can write it like that. 2H is equal to the geodesic curvature of gamma in M, and this is with respect to the unit normal eta, that is 1 over mu times 1 over mu, blah, blah, blah. This is the mean curvature. So it's the geodesic curvature minus something, depending on mu. Okay, but then what you can see is that this number on the right side, that is here, in fact, is the geodesic curvature of gamma with respect to this conformal metric on M. So if you change the metric on M by mu, then you have that the curvature of the cylinder is 1/2 of the geodesic curvature of the curve above which you are doing your cylinder. That is usually the curvature in R3, the curvature of the cylinder is exactly 1/2 the curvature of your curve. Here is 1/2 the mu curvature. You can call it the mu geodesic curvature. In fact, we will call, when we do computation in the metric mu, we will call mu something. So this is a mu geodesic. So the cylinder is minimal if and only if gamma is mu geodesic, because this curvature is 0 if and only if k tilde g is 0. So gamma must be a mu geodesic. R3, a cylinder is minimal, that is, it is a plane, if and only if it is a cylinder over a straight line. Okay, so mu geodesic is going to take the place of geodesic. Okay, so I want to stress here the fact, I don't know if we will reach this point today because we are already very late, and I don't know, I'm very slow. A minimal vertical cylinder is not necessarily error minimizing. And this is important. In R3 it is, because the plane is also error minimizing. Here it isn't in principle. Okay, so let me at least give you the statement of the theorem. It's we have to work a little bit more because we have to choose now. Before, the Jenkins-Serrin domain was a polygon with some convex side. Here, you know, M can have genus and so on. So we have to be a little bit more careful. So a relatively compact domain omega in M is, say, the Jenkins-Serrin domain if the boundary is a piecewise regular curve composed by mu geodesic open arcs or simple closed mu geodesic A1AR B1BS and mu convex curve C1 CM. Okay, so of course convex means with respect to the inner normal and all the endpoints. And also neither two of the AI nor two of the BI meet as a convex corner for the same reason. But here we also have mu geodesic open arcs. Simple closed mu geodesic. Not only open arc, but also closed mu geodesic. You will see an example, a picture in a short time. Okay, so usually when there are no CI components, the usual assumption always was that neither the union of AI, neither the union of the BI is connected. That was for free in the Jenkins-Serrin case because we were in R2, but in other spaces, this was not always for free, in other product space and so on. But we don't need it because we use a different kind of proof. The only place where this was not assumed was this paper by Eichmar and Metzger, and here you can always guess which is the journal, JDG. I'm sure, Journal of Differential Geometry, of course. But in this case, they were doing something. In fact, they were solving a different kind of Jenkins-Serrin Young equation. So it was, and the proof for me is very mysterious. So I don't know. But it was a product space in their case too. But it was the only case where they did not assume this condition on the connection. Okay. So Jenkins-Serrin problem, you all know what is it. I told you before many times. So just one more notation. What is a polygon inscribed in this kind of domain? It's not hard. It's the union of disjoint curves satisfying the following condition. P is the boundary of an open and connected subset of omega. Each gamma j is a closed mu geodesic or a closed piecewise regular curve with mu geodesic components whose vertices are among the vertices of the endpoints of AI, BI, and CJ. And again, for such an inscribed polygon, you will have a picture in a while. For such an inscribed mu polygon, we define the length as before. Alpha is the part of the polygon that is the part of the AI. Beta is the part of the BI, where it is minus infinity. And gamma is the length, the total length of the polygon. Everything computed in the mu metric here. Okay, an example. I took a Costa surface because it's a nice surface. And then, for example, the polygon can be the one that is bounded by B1, B2. No, B1 is here, B2, A1, C1, C2, A2. Okay, this is the domain. And then a possible inscribed mu polygon is the union of these gamma I that are 4. And for example, gamma 1 is L1 plus A2 C2. And then you have gamma 2 that is just L2, this one, L3, and then you have to close, and you close with A1, for example. So the bottom part of the bottom, and I mean, there is also a part of the planar part that is excluded. This is a possible polygon. So an inscribed polygon. So as you see, I mean, it's the picture is just a picture. I mean, because mu is arbitrary, so I'm not telling who is mu and why these are mu geodesic, for example. Just a picture. It's very general picture, but it can be a complicated stuff. Jenkins-Serrin theorem, here again. you have a Jenkins-Serrin domain as we want. If the family Ci is non-empty, then the Jenkins-Serrin problem has a solution if if 2 alpha is smaller than gamma and 2 beta is smaller than gamma for all inscribed mu polygon. And in this case, the solution is unique. So exactly the same condition as Jenkins-Serrin, but with a mu length. And if the family is empty, again, it has a solution if this condition hold, 2 hold, for all inscribed polygon, and also if the polygon is the omega, the complete domain, then you must have alpha equal to beta. And the solution is unique up to vertical translation. Okay, so again, Jenkins-Serrin already knew everything because it's really the same theorem. And in fact, I have to say that our first motivation was to solve this problem in the Heisenberg space. And then we realized that in Heisenberg, that is not a product space. We had to do something else with respect to the other. And we finally solved the problem in this much more general case. Okay, the condition is called the Jenkins-Serrin condition, but all these conditions are called the Jenkins-Serrin condition. Okay, so the proof. How much time do I have? Because I started later, so please.
I think we started at 8 or 9 after. You have like maybe 13 minutes.
Okay.
Is that okay?
It's okay. It's perfect. Okay, so an outline of the proof. So how you have to construct a solution that have infinite boundary value. So it's very natural to construct this as a limit of finite boundary value solutions, graphs. So you start with the plus n where you want to go to infinity, minus n where you want to go to minus infinity, and then you're prescribed on the CI when you have a prescribed boundary data, you truncate it at n, so that your solution will stay between n and minus n. Okay, so you have to prove first the existence of this, that in R2, in R3 it's easy, but here it's not so easy. But anyway, you have to prove this existence, so it's a PDE stuff. And then you have to show that a suitable subsequence converge uniformly on compact set and achieves the desired boundary values. This is what you want to do. But then there is an issue, because as you have part of the boundary that goes to infinity, there may be a subset of omega where the subsequence do not converge, or the limits gets infinite value. Okay, you don't know. Your infinite boundary value can enter in your domain, and then you have a problem. But in fact, so you assume, okay, it can go to infinity somewhere, and then you study the shapes, the possible shapes of your set that you can call divergent set, where it goes to infinity. And in fact, you can show that it has a very special shape, and then you can show that if it is different from the empty set, then you have a contradiction with the Jenkins-Serrin condition. So in some sense, the divergent set, if you have some divergence inside, this goes to the boundary and you get a contradiction with the Jenkins-Serrin condition. Okay, this is the general idea of the proof. So let me say some more word about that. And then, of course, you have to show uniqueness, but this is just a generalization of the maximum principle for unbounded solution. You have to do it, but it's not, I mean, it's a standard stuff. Okay, so let me talk a little bit about the existence of this finite solution. You can use, as I told you, you are looking for this kind of solution, plus n minus n prescribed, and you can use Perron method. There is no convexity assumption. You just need a subsolution and a super solution, and these are the minimal sections. They exist, so you can take the minimal section of your projection. And then, in order to prove that the solution take the right boundary value, you need some barrier at any boundary point. And this is a Perron. It's just Perron. You just need subsolution, subsolution. It's very classical, and good barriers at the boundary. And good barriers, in fact, are given by Scherk-type solution, Scherk-type surfaces. One called them Scherk-type because are defined on small triangle and has plus infinite boundary value on one of the side of the triangle. And here, in R3, Jenkins and Serrin had the true Scherk solution. I show you Scherk solution on a square, but if you divide the square in 4 with a diagonal, you have a small triangle, 0, 0 boundary value plus infinity on one of the side. Here we have to work much more, and also we don't have large Scherk-type surfaces. We only have a very small Scherk-type surface, so this very small triangle. But it's enough because the barriers at the boundary point to prove that the solution take the right boundary value are local, are at any point. So it's good. We can solve this. Okay, and now we have to study the convergence of this solution UN that we have found. Okay, so in order to study the convergence of a subsequence, one needs to understand the subset D where the sequence could diverge, as I told you before. So you call C the set where it converges, where it, at least where it is bounded. That it is omega minus D, of course. And now you can work a little bit, and you can, in fact, replace this C where UN is bounded with the set where the gradient of UN, the norm of the gradient of UN is bounded. Why? Because for this kind of solution, this kind of surfaces, let's say, or this kind of functions, solutions, one have local uniform gradient estimates, some Arnack type estimate that depends on this the estimate given by Rosenberg, Swam, and Tubiana, again, JDG, Journal of Differential Geometry. One can prove that if you have a point where UN is bounded, then there is a subsequence of UN minus UN of P that converges on the connected component of C in omega that contain P. Okay, so you do a slide back sequence. You put UN minus UNP, and this converge. But then C, you can also prove that C may be identified with the subset where the gradient is bounded. Okay, so I'm a little bit sloppy here, but you have to think about this fact. You can replace C with the set where the gradient is bounded. Of course, this makes you really free because you want to treat solutions that are going to infinity. So in order to get the convergence, this can be very hard. But if you keep the solution translating at a single point, I mean, you translate you translate vertically UN by minus UN of P, then you have everything passing through at the same point, and you just have to study how vertical this becomes. Okay, so you transform this set in the set where the gradient is bounded. And then, of course, you transform D in the subset where the gradient is unbounded. So the divergent set, in fact, is where the gradient is unbounded. And then when P is in D, as the gradient is unbounded, up to subsequent, you produce as a limit surface a vertical minimal cylinder on a curve. So when the gradient is unbounded, it's going to be vertical, so it's a cylinder in the limit. And thus the mean curvature of a vertical cylinder on gamma is this one, then we wrote that before, it was 2h equal to mu, the mu geodesic curvature. Then you know that this set where you are going to infinity must be a mu geodesic. So in fact, the divergent set is a union of mu geodesic that are called the divergence line. So here comes the characterization of divergence line by Mazzei, Rodriguez, and Rosenberg. Then also we talk a lot with Maddalena for more properties about this divergence line. And in fact, the structure of the divergent set, that is the union of this mu geodesic, one has to study it and it's not very simple to study it. Once you know that the divergent set is made by mu geodesic, you have to study them. And to study them in a general Killing submersion, it's not very simple. In fact, they are mu geodesic on your manifold M, on your two manifold M. But for example, you can have this kind of situation where the geodesic accumulates, for example. They can be uncountably many, may accumulate, and so on. And this is a little bit wild. But then you can work a lot and prove that, in fact, you have only finitely many connected components outside D. And no divergence line can be isotopic to one of the AI on BI. Let me show you a picture. So your divergent set is made of mu geodesic, and the complement has only finitely many connected components. And for example, as you cannot have some divergence line isotopic to AI or BI, for example, this red one cannot be there. Okay, it's not a possible mu geodesic belonging to the divergent set. So you have a very precise structure of the divergent set that is a mu polygon, in fact, an inscribed mu polygon, even in this case. Here it's the picture is a little bit more complicated because but the idea is exactly that. It's a mu polygon. Okay, I'm running out of time. I just have 2 or 3 minutes. 3 minutes. So I'm not going to explain how why the length of the sides of the polygon is enter in this place, because you have Jenkins-Serrin condition is about length. So how the lengths are in this proof? In fact, I can say that the length is because the fact that you are going to plus infinity with your gradient show you that how to say it, show you, I'd say the magic word, the flux is the length. And the flux is something important related to our equation. Okay, this is, you see, this is a very important part of the minimal surface equation. So the length enter in the place like that. I'm not going to say more details about that. But this was also in the case of Jenkins and Serrin, of course. But the key point here is to treat the gradient and not the solution, because Jenkins and Serrin need to do a different proof, exactly because they were not looking at the gradient, but they were looking where the function was going to infinity. Okay, so just I skip this and I finish just with an example. You take a rotational onduloid. You take mu equal to 1 and tau equals 0. Okay, it's just a simple case. And then you take these A1, A2, B1, B2, and B3 that are geodesics here. Now, you can consider your Jenkins-Serrin problem in different cases in this onduloid. For example, take the domain bounded by A1 and B1, so these first two, and you ask, is it solvable Jenkins-Serrin. Is Jenkins-Serrin problem solvable? Yes, it has a solution. Why? Because any possible closed simple, here, look at that. Here you just have A1 and B1, two closed geodesic in the boundary. So you don't have vertices, you don't have convex part, you just have these two boundary boundary curves. So your inscribed mu polygon can be also can be only formed by mu geodesic inside. Okay, so any mu geodesic here have length that is larger than the common length of A1 and B1. It's just you see the shape here. So it has a solution. Okay. On the contrary, for example, if you consider the two maximal A2 and B2, then any mu geodesic here is shorter, so you don't have a solution. And that's it. I mean, it's. I think I can stop here and thank you again.
Thank you very much, Barbara. Thank you for this nice talk. Let me ask you, before I ask the audience to ask you questions, let me ask you a couple of things. In these last examples that you showed, you're always assuming, like for instance, this onduloid. This is the base, right, of the submersion. You're thinking of a product by R.
Yeah.
Onduloid times R.
For example, yes.
Or anything where the onduloid is the base of.
In fact, you can consider any case where mu is equal to 1, and tau anything where the onduloid is. I mean, the picture is like that, but you can consider any kind of structure where the onduloid is your base.
Okay, of a base of a killing submersion.
Yes.
Okay. One thing that I wanted to ask you is this. There's an assumption that the length of the flow lines of the killing field should be infinity, right?
Yes.
And this is because when you solve the equation, you want to make sure that you can go as far as you want along the flow lines. Correct?
Yes. Yes.
Okay. It seems to me that what you really need is that the killing field is complete, which when the flow lines of the killing fields are homeomorphic to R, it is the same as having infinite length.
Mm-hmm.
But on the other hand, you may have circles.
Yes.
In this case, you may obtain surfaces which are not embedded, but they have self-intersection.
You are right. Absolutely. Absolutely. You can do it, in fact. You can do it also because what you can do if you have, you can take the universal cover.
Right, for instance, or some cover. Yeah, maybe not the universal one, but
yeah, or some cover. So you are absolutely right. This is just a simplification.
Right.
But because as you're looking for a graph, you prefer to have something.
Yeah, I'm saying this because there are nice examples of this. First, for instance, you can consider S3, which is fibered over S2.
Mm-hmm.
And in this, the Hopf fibration.
Yes.
And the field tangent to the circle, to the fibers, is killing.
Yes, that's true.
So you may obtain something in spheres, in S3.
In some non-embedded solution in S3.
Non-embedded solution which has the topology of S2, I think. Because the topology of these surfaces is always the topology of the base manifold, isn't it?
No.
Well, at least
I mean, of the polygon that you are considering.
All right. So the polygon in S2, correct. Yeah, that's right.
So this is,
and then there's also other examples. SL2R.
Yes.
Fibers over the hyperbolic plane, right?
Mm-hmm.
So maybe, but I think the fiber are circles.
But that's not a problem because you, as you thought, I mean, you can consider again. You can consider the universal cover of it.
Right, right.
But
So
you are right that all those spaces are examples. You have only to as I told at the beginning.
Every homogeneous three manifold has this.
Yeah.
This.
Anytime you have a, not every homogeneous three manifold, I think you need. You say you need to have a Killing vector field, non-zero, such that, as I told at the beginning, I'm not sure. I mean, I'm not able to prove that every homogeneous three manifold.
Isn't there Thurston classification? If the isometry group has dimension 6, it's a sphere.
Yes.
There's nothing with dimension 5. If it's dimension 4, it's the Heisenberg space.
Yeah. No, simply connected. You mean simply connected?
Right. Yes.
Okay, simply connected. Yes. You're right. Absolutely.
Yeah.
Oh
yeah, like a Sol 3, for instance. Yes, Sol 3 is another one.
Nil.
Right. Nil is Heisenberg, right?
Yeah, Nil is Heisenberg.
This is the original problem that you wanted to study.
Yes, we started with that. And then we realized that in order to solve in Nil, we have to work more.
Okay, please allow me just one more question.
Yeah.
So you said in the minimal case, if you have, suppose you prescribe plus infinity on an arc, then there's no solution, basically, because then the mini surface should take value infinity also in the convex hull, right?
Yes.
Which is probably the reason why you never want the union of two A's to be connected, because
exactly,
problem, right?
Exactly. Yeah.
Right. Do you have the same problem for constant mean curvature when the mean curvature is different from 0? Do you still have the same problem?
You have the following. You have that your boundary curve when you are going to infinity must have curvature twice
the mean curvature.
If not, you are going to infinity. It's the same. You cannot prove convergence.
Okay, I get it. Okay, thank you very much. Yes.
You're welcome. It was
I apologize with the audience for taking all the time for myself. A real good host should not do this. I'm sorry, but please feel free to ask questions to our speaker if anybody is interested.
Yes, I have a question. Hi. So the boundary conditions in the statement of the theorem of Jenkins-Serrin say that so they have to be continuous besides the infinities, right? There's no room for discontinuities.
I'm not able to listen correctly. May you repeat it, please? I'm sorry.
Yeah, sorry, I might have some connection issues. I'll say again. So I was asking, the boundary conditions in the Jenkins-Serrin theorem, they have to be continuous. There's no room for discontinuities, is there? Is this an essential thing?
I mean, no, it's not really essential. They can be piecewise continuous as well. But it's a little bit, I mean, no, there is a, when you have a minimal surface and you have a discontinuity at the boundary point, then the segment between the two, you have a discontinuity, and then you have a different height for above a point, okay? Because you have a discontinuity. So the segment between the two height is contained in the boundary of the surface. You see what I mean? Okay, so you can allow this kind of thing. There is no problem, because all the theorem that you can prove about existence of minimal surface and so on, you may allow this piecewise continuous on the function on the boundary, provided that you allow your solution to have a vertical segment in the boundary. I mean, you have to accept this as a boundary part. You have to add this boundary part.
Yeah. Okay, but you can have a finite number of discontinuities.
Yes, discontinuity. Yes.
Okay. Thanks.
Thank you, Paul, for your question. More questions for Barbara? Comments? Did you think of any application that goes along the line of the proving the existence of some conformal mapping between, I don't know, strange spaces like Harold Rosenberg and I can't remember his
Pascal Collin. No, in fact, no. Could be interesting, yeah? Could be interesting. Because
yeah, in the case of the constant mean curvature, of course, the projection is no longer
harmonic.
No longer harmonic, right?
Right. But here we have.
Excuse me. I have Stefano Nardulli who is calling me.
You can
Sorry. So in the case of the constant mean curvature surfaces, the projection on the base is no longer harmonic, I think.
No.
Yes, Enrique. Yes, Stefano only calls on video. Yeah.
Ah, okay, on video.
Yeah.
Say yeah. You can call him in the.
I can put him on screen now.
I will be glad. I know that he is coming to Italy by the end of the year, so I suppose I will meet him here. No, anyway, yeah, it
Okay,
could
so
be interesting
he's sending me WhatsApp messages now.
I don't know how to say it in English. It's invasivo. No, it's no more harmonic, but it's very interesting because here we have minimal surfaces in these spaces, so it could be interesting to find. But you know.
But also, wait a second. Is it true that it's not harmonic? Like the coordinate functions of a constant mean curvature surface are not harmonic in general, right?
No.
Only if it's minimal.
Yes, but here it's not really, you know, of course, if you have a minimal surface in R3, the coordinate function are harmonic, and here you have to, here you have, not here, but in the case of Collin-Rosenberg, they were harmonic with a conformal structure of the surface.
Yeah, that is another problem. That I have no idea how they can prove it. Like,
no, this is classical. I mean that if you take the
graph of a function which is harmonic has the structure, the conformal structure of the complex.
In that case, I see what you mean now. I understood. I didn't understand correctly before. So you want to say, how do they prove that the conformal structure is C?
Right.
This is not easy to prove. No. You're right. I don't remember exactly.
I have no idea how that could be obtained. I understand that the projection is harmonic, of course.
Yes. Yes. No, I mean, I don't remember that. I have to confess now at this moment, I cannot, but it's not simple. You can see that it's quite different from H2 because, you know, how it is the construction. How is the construction? The construction is that you have plus infinity minus infinity on the sides, and then you increase the number of vertices. And when you have plus and minus infinity, as I was answering in some sense to Paul, you have on the vertices, you have all the straight line included in the boundary of the surface. Mm-hmm. So when you increase the number of vertices, you have many straight lines. So you change completely the conformal structure with respect to H2.
I see.
At infinity, I mean. Yeah? But I'm not able to tell more than this. But you can imagine a surface, a graph, that have a lot of things at infinity, finally.
Yes.
But I mean, okay. I don't know why. See, but this is one of the hard part of the paper.
Thank you. Would anybody like to ask more questions to Barbara? Take advantage that she's online. If not, maybe we can thank this. Oh, no, there's a question. Please go ahead. Thomas, did I see some Thomas? Thomas Silva. Sorry.
No, sorry. Okay.
Misclick. Okay. No problem, Thomas. Okay, so thank you very much. Let's thank the speaker. There was a very good.